Hello, and thank you all for coming the Silo Seminar. It's my great to introduce our friend colleague Alberto Del Pia, who's a professor in the Industrial and Systems Engineering Department and also a WID faculty. I could go on and on about Alberto's many awards. He recently won the Egon Balash Prize, which is given to a mid-career researcher in optimization, international award. What else do you win? He won the Informs Computing Society Prize, which kind of cheeses me a little bit because typically Alberto doesn't really do very much computing. He's more of a methodological. Most of his, contributions have been more methodological. So he can even do computing. But I think the greatest accolade that I can give Alberto, I just saw, and Steve knows this story too, is I just looked up. Kyle Cranmer did a software tool that tried to connect experts at University of Wisconsin to different experts and other people. And so you can do a keyword search on who is the biggest expert in any subject at Wisconsin. So of course I went there right away. And what AI told me is that if you want the number one expert in optimization at the University of Wisconsin, you have Alberto Del Pia. So we are absolutely delighted that the number one expert in optimization will tell us about minimizing quadratics over integers.
This great, can you hear me? Yes. For this great introduction. Yeah, thank you so much. It's really nice to give a Silo talk. It's nice to see so many of you here. I'm going to talk about minimizing quadratic over integers. This is my probably, yeah, one of my main, by far one of my main directions of research, and I really enjoy it. And it's also something that kind of defined my career so far here in Madison. I remember when I arrived here, I just wrote kind of the first paper about this topic, and also during the interview, somebody asked me, "But Alberto, what do you think people will know you for? What would you like people to know you for? When you're a few years down the line?" And I remember I said exactly integer quadratic optimization. And so yeah, I guess luckily we managed to obtain some interesting results in these years, and I'm excited to share them with you. So what I want to do today is tell you a little bit about the problem, so how this optimization problem looks like. I want to tell you a little bit about some structural properties of this problem. And then I also want to tell you a little bit how we can use this structure in algorithms to solve efficiently some of these problems. Feel free to stop me anytime if there's anything not clear. I'm happy to discuss. Good. So this is the problem we're going to look at. So we call it mixed integer quadratic programming, MIQP, and essentially we have a set of points we are considering, which we call the feasible region. This is the set of points or vectors in ZP times Rn minus P. So you see we have some integer components of my vector x, the first P, and then the remaining are continuous. And we look only at these points inside a polyhedral region. So it's a set here, you see, defined by finitely many linear inequality constraints. And so far, you see everything is linear. This is the feasible region also of what you see in mixed integer linear programming, which we study also in class. And the key difference with those linear problems is the objective function. Here, we want to minimize a general quadratic function, which without loss of generality, you can always write in the form x transpose qx plus c transpose x for some symmetric matrix Q. We're not going to assume anything about the quadratic, anything about convexity or not. It's just a general quadratic for now. The data of your problem here, essentially what is given to you, consists of your matrix Q, your vector C, your matrix A, and your vector B. So this is what I call the data, and we assume it's going to be rational, meaning that all the components of these matrices and vectors are rational numbers. And some of the results I'm going to talk about also work if you have real data. Some don't. But yeah, let's just stick with the rational case. And specifically, since we're going to be interested also in algorithms, we definitely need to assume rational data to have any meaningful analysis in a Turing machine setting. All right. What else can I tell you about this? Yeah. So what we mean in optimization when you read an optimization problem of this form is that our goal is to find some vector, at least just one vector in the feasible region which minimizes the objective function. So that's the goal. So essentially we want kind of argmin over here. I want to find one point there. We don't need to find all the optimal solutions. So that's kind of the overall goal. So we're going to talk more about this. Good. So this problem contains special cases, two very well-known classes of optimization problems, which I like so much. And they are mixed integer linear programming, which again we study in class. And it's the case where the objective function is linear. So for example, when the matrix Q is the all zeros matrix. And it also contains quadratic programming, continuous quadratic programming as a special case where you have p equal to 0 here and all variables. So no variable is restricted to be integer. And these are two very well-established fields of research. Mixed integer linear programming is currently still a very successful area of research with many people actively working on this problem, and well, again, we know so much about this problem that we teach courses about it. Quadratic programming is a bit less active, I would say. We have some wonderful results, especially from the 90s, but yeah, recently not many people have been working on it, but it's been a very successful field of research. What Jeff told me, and I always mention this in my talks and proposals, is that this is a prototypical mixed integer nonlinear programming problem. So these are a huge class of optimization problems called, in a way, MINLPs, where you can have any type of nonlinear function, integer variables, and they can be extremely complex, of course, and they mirror nicely, essentially, every real-world problem that you can look at, optimization real-world problem. Of course, we know very little about MINLPs due to their complexity, but MIQP is a very nice step towards our understanding of MINLP because it contains both its sources of complexity in the simplest possible form, which are integrality of some variables and nonlinearity of functions. And in this case, of course, we have only one nonlinearity in the objective. Yeah, but this will be enough to confuse us. Good. So, as I told you, mixed integer quadratic programming contains a special cases mixed integer linear programming and quadratic programming. Both these fields of these optimization problems is well known that they have a huge number of applications. And so, of course, MIQP contains all of them and contains many more because you can combine both integer variables and quadratic objective functions. And so here I just listed some some applications, but also, yeah, but then there are many more. I don't want to talk about this. I'm not an expert in applications. So if you have questions about this, yeah, you can ask Jeff. Great. So instead, let's start to talk about the structure of these problems. And let's just warm up with a nice picture, okay? This nice picture, we have it's a two-dimensional problem, so we're in R2. Here, both variables are required to be integer. So and our polyhedral region is given by this pentagon with, like, say, 5 linear inequalities. And so our feasible region, the set of points over which we want to optimize, is given by exactly the dots that you see here, right? All the integer points inside the polyhedron. Then the two curves here represent instead a level set of my quadratic objective function. So all the points in the union of these two curves have the same exact objective value. And if we're in the case where the points between the two curves have higher objective value than the curves and the ones outside have a lower objective value, then you can see that this is the optimal solution, the unique optimal solution to this problem. And if you're familiar with both mixed integer linear programming or quadratic programming, you immediately see that, yeah, things can become more complex than in those fields, in those optimization problems, just based on these pictures, because, yeah, based on what we know from the other problems. Yeah, anyway, this is just a picture. Any questions so far? Great. Of course, by the way, in this picture, the quadratic is indefinite. It has a one positive and one negative eigenvalue. Okay, so let me then state in this slide three fundamental properties of MIQP problems that I find very interesting. So the first one here says that the problem is unbounded if and only if there exists unbounded ray, an unbounded ray. So essentially, we often, sometimes our first goal algorithmically is to understand if the problem is unbounded. What do I mean with that? If there are points feasible with objective value arbitrarily small. And, what this property tells me is that if the problem goes to minus infinity, so if it's unbounded, then it goes to infinity in the simplest possible way. So essentially, there exists a half line such that the feasible points on this half line go to minus infinity. So it's a very simple one-dimensional structure, right? And it's really the simplest you can have. Now, the second property instead claims that infima are always achieved. So in fact, this justifies the notation I've been using here, because you see, I wrote min here, assuming that this function does have a minimum on this infinite set, but of course, well, we don't know it right away. But luckily, thanks to this property, we know it in fact, and so I can write min instead of infimum. So yeah, this is also great. It tells me, that this has an optimal solution if it doesn't go to minus infinity. Also, the last property here tells me that any such problem has optimal solutions of polynomial size. So what do I mean with size? Size of any kind of vector or matrix is, think of it as the number of digits you need to write it down. And what this is saying is that you don't need many more bits to write. So right, essentially that your numbers here don't explode in a sense that that the size of the optimal solution, so the number of digits of it, is only polynomially bounded by the size of the digits here, of the numbers here, so of the number of digits here. Which is, it's kind of technical, right? Maybe a little bit confusing, but this is fundamental if you have any hope of developing any efficient algorithm for this problem. Because you see, think about having to solve this problem. Let's say you know right away what is the optimal solution, so let's even forget about how difficult that is, but even just to output the solution, if you don't have this property, so if you can have optimal solution of exponential size, then even just writing down the optimal solution is exponential time. So yeah, so you have no hope of finding an efficient polynomial time algorithm. In particular, this property implies that this problem essentially lives in the famous complexity class NP from the is P equal to NP question. Yeah.
So anything that has nothing to do with the rational assumption of the data.
It does. It does. So actually, good question. Good question. I'm not sure in the irrational case if that's true. Yeah, I never thought about that. But the result assumes rationality. Yes. Yeah. Yeah.
And then I had a question too, which is maybe naive.
Sure.
Coming from the fact that you're allowing your queue to be indefinite.
Yes.
I mean, usually my mental image is that there are rather delicate questions coming from looking for integral solutions. Like if I'm like, I want to know whether, x squared minus 23y squared can equal 2 or something. That's like a very delicate problem. So why does that not get in the way? Often you do have to go to an exponentially sized.
Yeah, I will talk about that. Just in a couple of slides. It's a very nice connection. Absolutely. There you have an equality constraint, right? A quadratic equality constraint, which makes things very complex.
All these problems go away. I love just one. Okay. Okay.
Great. Thanks. So, okay. So anyway, you see these properties, we came up with these properties like 10 years ago or so in one of the very first papers about this topic that we wrote. And at the time, you see, if you're familiar with mixed integer linear programming, you're really familiar with these properties because, of course, well, they hold also for the special case mixed integer linear programming. And in fact, they're generally also studied in class. And So at the time I thought, yeah, sure, they extend to this problem, great. But really kind of the more time, the more I work on this problem, the more I find it surprising that they hold. Because essentially, as soon as you try to make this problem now slightly more general, they all essentially fail. And so, yeah, it's kind of strange to me to look back at these properties because, yeah, at the time I didn't really think they were kind of so special. But so on the one hand, this tells me it's unfortunate that they don't extend to more general settings, because of course we would love that. On the other hand, it tells me that these are really, that it's great that they hold for MIQP, and it's great that we can use them to also develop efficient algorithms and whatnot. Okay. So I want to convince you, or at least tell you a little bit about this. And so what I want to do now is focus on one of these properties, the third one, and show you how this fails as soon as you make the problem more general. And of course, you can do this in several directions. So let's talk briefly about that. So this is a little bit more formally the statement. So it says of the third property we saw, it says that if this problem has optimal solutions, then it has an optimal solution of polynomial size. Of course, how can you now make the problem more general? Remember, our goal is to make the problem more general and see that this does not work, that you can have only solutions that are not of polynomial size. So one way is to make the objective more than quadratic, let's say cubic. Okay, so but then we can look at this very simple problem. It's just a two-dimensional optimization problem, both continuous variables and just a box constraint essentially on them, and you want to minimize this cubic. You can easily see that the unique optimal solution is this irrational vector 2 to the 1/3, 2 to the 2/3. And how is this obtained? Well, really, this point is just a local minimum of the cubic, and everything we're doing is just chopping off everything, yeah, making it a global minimum by removing everything far away from that point. And then, of course, then in this case, this implies that this has a unique optimal solution, and it doesn't have polynomial size because it's irrational. So trivially, it has kind of infinite size if you think about the number of digits required to write it down. All right, so this immediately tells me, fine, let's stick with quadratics and not make not consider polynomials of higher degree. And so what can we do with quadratics? Well, we can add quadratic constraints. Now, it's well known, it has been proven in 1973 that as soon as you add even just a constant number of quadratic inequalities, the problem in the impure integers variables, the problem becomes undecidable. And this has been proven by Jarrett's law. It's a consequence of the solution to Hilberstein problem completed by Matjasevich in the 70s. And so this doesn't only tell me that we cannot bound the size of smallest optimal solutions by a polynomial, it really tells me that I cannot bound the size of smallest optimal solutions at all. So again, also in this case, you see that this property definitely doesn't hold as soon as you add a fixed number of quadratic inequality constraints to the problem. Okay, fine. But let's say, what if we add just one quadratic inequality to my constraints? So I have all linear inequalities, and let's just add one quadratic. And we see that also here, this property fails. And for this, we need a little help from number theory. So we look at Pell's equation, which is this equation, x squared minus ny squared equal to 1, where n is some parameter. And you're searching for for positive x and y that satisfy that equality constraint. So you can kind of visualize it here. You have this quadratic equality constraint. So you want to be on this curve intersected the positive numbers, and you're looking at integer points in here. So this is a well-studied equation. And in particular, one result that I'm interested in is that there are families of this parameter n. For example, 5 to the 2k plus 1 for k positive integer, for which the smallest solution to Pell's equation has size omega of 5 to the k. And this is very close to what we want, you see, because here the input size is the size of n, which is linear in k. But here, the smallest solution has size that is exponential in k, right? The only thing we have to do is kind of now massage this Paz equation to make it fit our optimization setting. But it's extremely simple. Everything you have to do is, well, you keep your, of course, xy positive integer here, which you can write like this, of course. And now you just split your equation into two. Because remember, I promised you I would use only one quadratic inequality, right? So we split it into two. We add among the constraints one direction, and we minimize the same left hand. So that, since for our family of parameter n, we know that there are solutions to Pell's equation, we know that the minimum is exactly at the for points that satisfy this set equality, and then the optimal solutions are precisely the solutions to Pell's equation. And so then we know that this problem has only solutions of exponential size. Good. And you see, this problem is just in dimension 2, only with integer variables. Okay? So I hope with these examples, I convince you a little bit of how things get complicated, as Jordan was suggesting, right? Very, very quickly. So do you have any question about this so far? Oh, great. Yes.
I'm not even sure how to phrase it, but what does this then say, like, about near solutions or near minimizers? Like, is it saying that there are things that are very close and one's great and one's horrible or something, or what? Yeah.
Well, about approximate solutions, you mean? Yeah, it doesn't really tell you. I mean, directly doesn't tell you anything. And we, in fact, yeah, we don't really know. Yeah, of course, it's a very good question. Yeah, one in general, in that case, we'll ask for an approximate solution.
How to say, like, we wouldn't really know how much accuracy we need.
Right. Yeah, yeah, that's a very good question. Yeah, it's unclear. So, yeah, you might still be able to have a good accuracy, but yeah, you have to understand that we don't know.
I mean, if you know a lot more about guaranteeing that there was like a small value of like 4 or 5 or something, but.
Okay, great. So then let's now talk about algorithms. So what I want to do is tell you a little bit about what is known about exact and approximation algorithms for these problems. And then I want to tell you a little bit about our latest algorithm, because I just want to, of course, give you the main idea, because I want you to see the techniques that we use and, yeah, what we do. Good. So there are several known algorithms in fixed dimension. So what does it mean? So, first of all, I'm interested in polynomial time algorithms, right? So with a polynomial runtime, so efficient, theoretically efficient algorithms. And first, we discuss the ones in fixed dimensions, which means that this runtime can have n in the exponent, but that's the only thing besides constant that you can have in the exponent, okay? This is always, I mean, in this kind of complicated settings, it's always pretty much the first thing you look at, right? The fixed dimension. So we have exact algorithms only in dimension 1 and 2, and we have exact algorithms in if you have a convex or concave objective. Also, we have another exact algorithm if you have unary encoding on some of the input data. And I don't want to enter into details here. It's pretty technical, but yeah, go ahead.
Why do you discuss concave and convex case separately, or are they the same?
No. Because you can think of it in the convex case, you will have solutions in the kind of interior of the feasible region, and in the concave instead you look at pretty much the boundary of the convex hull of them. So it's very different actually. Yeah. Yeah, remember, I'm assuming I'm minimizing, right? So I'm minimizing a convex is what you would think generally is easier, but I mean, due to the integral variables, it becomes possibly complex too. Okay, so this is what we know about exact algorithms in fixed dimension, as far as I know. Then we know a few approximation algorithms, very interesting. And later I will tell you more what we mean exactly with that. But we have a beautiful approximation algorithm by De Loera, Hemmeck, and Weismann, which is just, that's it, doesn't require any other assumption. And then we have another one which requires instead a homogeneous objective, which is essentially almost convex or almost concave. The fact I'm also listing this other result is because it uses a stronger notion of approximation than this. So it's not implied. All right, so, and this is what we know about fixed dimension, but what do we know about non-fixed dimension? You see, as soon as you have a non-fixed dimension, even just finding a feasible solution for this problem, even like forget about your objective function, just being able to understand if there is a feasible solution or not, and if there is, finding one is already NP hard, so we cannot do it in polytime unless P is equal to NP. And so if we are not in fixed dimension, we need some assumptions just to be able to deal with the feasible region to, of course, be able to at least find a feasible solution. Otherwise, there's no point in trying to optimizing our objective, no matter what it is. And so in general dimension, you see the assumptions that we have here in this kind of 4 results. On the left, in red, we have the assumption that exactly make sure we can find feasible solutions efficiently, which comes directly from mixed integer linear programming, because this has nothing to do with the quadratic function. So the most well-known classes of mixed integer linear programs that can be, for which you can solve this feasibility problem in polytime are when you have a totally unimodular constraint matrix, or if you have a fixed number of integer variables, while you can have a general, any number of continuous variables. And also, if you have a totally bimodular constraint matrix. So you see these red conditions are really just about that. You need them to be able to deal with the feasible region somehow. Okay, so, and the other assumptions instead that we have here in our algorithms are really about the objective function. So we have exact algorithms if we have a totally unimodular constraint matrix and a separable convex objective, thanks to Ockbaum and Shetty-Kumar. Then we have another exact algorithm if you have a fixed number of integer variables and a convex objective. Then we have a couple of approximation algorithms. The first one says that if you have a totally bimodular or totally unimodular constraint matrix and a separable concave objective of fixed rank, you can also find obtain an approximation algorithm. And finally, if you have a fixed number of integer variables and an objective of fixed rank, so very general, possibly indefinite. And this is the result I want to tell you a little bit more about. It's one of our latest results.
What does fixed rank mean?
Right, where the matrix Q in the objective, the quadratic matrix, has fixed rank. So if you have a fixed number of non-zero eigenvalues.
Okay, but the n can grow.
Right, right.
Separable is like completely separable, like f of x1 plus f of.
Separable, we mean that you don't have mixed terms xi, xj, right? With non-zero coefficients. They're only either xi squares or xi's. Good. Okay, great. So, of course, since I'm going to talk about an approximation algorithm, I need to tell you at this point a bit more clearly what is an approximate solution. So let's see the definition. We say that so pick any epsilon in 0, 1. Then we say that a feasible X diamond is an epsilon approximate solution if this inequality holds. So essentially, it means that the distance in objective value between your approximate solution and the true optimum, just this, is just an epsilon fraction of the full gap of the objective function on the feasible region. Okay? So for example, if you pick epsilon equal to 1, you're just asking for any feasible point. If you pick epsilon equal to 0, it's just global optimal solutions. And if you have like 1/2, it means that among, that you're searching just among the ones with the best half of objective values. So this, of course, there are several types of definitions of approximations depending on the problem you're looking at. But this is really, I strongly believe, this is really the only one you need in this case. Essentially, you need that such a definition has some invariance properties that don't allow you to cheat. So in this type of general problems, you can, for example, take any change of basis. And of course, you would like that if you perform a change of basis, you don't map, so your 1/2 approximate solution will be mapped to 1/2 approximate solution. So you don't cheat in this kind of silly way where you're just looking at the problem differently, but it's the same problem. And so this definition has this invariance property, so it's preserved under dilation and translation of the objective function, and it's insensitive to affine transformations of the objective function and the feasible region, like changes of basis. So this is the definition that has been used in the past by very smart people also for this type of general problems, and we're going to stick with it, okay? Great. And by the way, if sometimes most of the definitions of approximations, as you probably know, for combinatorial optimization problems are indeed special cases of this. Like, because you're going to know what is either the max or the min, and so you can kind of simplify this inequality and obtain sometimes, most of the times, another definition for your combinatorial optimization problem that follows on this. Not always so. Depends. All right, so, well, any question about this definition? Yes.
So does this allow, like, if the objective is necessarily, what if it's unbounded and goes to infinity, then like any solution is acceptable?
Oh yeah, good question. Perfect. That's a very good question. So if the problem is unbounded, you have an infinite range here, and so the definition really loses its meaning. And in fact, yeah, so that's not interesting in that case. Note that also one thing to point out is that in mixed integer quadratic programming problem, you can show that you can always restrict yourself to a bounded region, thanks to the third property we saw earlier, which immediately tells me that in this new problem, this will always be bounded. So, good. Great. All right, so now we can finally state the theorem a little bit more formally. That's the statement. We have that for every epsilon in 0, 1, there is an algorithm that finds an epsilon approximate solution to a bounded MIQP. The runtime is a polynomial in the size of the input, as you want, in 1 over epsilon, under the assumptions that, two assumptions, that the rank of the K of the matrix Q is a fixed number, and also the number of integer variables P is a fixed number. I'm particularly proud of this result because it's the first known polytime approximation algorithm for indefinite mixed integer quadratic programming, not in fixed dimension. So there are several technicalities that we had to solve and ideas we had to obtain to make it work. I also want to discuss briefly that how, in a sense, this result is best possible. So I claim kind of that the running time is best possible unless P is equal to NP. Well, of course, it doesn't mean much. I mean, of course, the runtime can always be improved in some way, but what I mean is that it cannot be improved significantly. What do I mean? For example, you could not, well, first of all, you cannot drop any of the two fixed assumption. Otherwise, you would have proven P is equal to NP. Secondly, for example, the runtime is the polynomial in 1 over epsilon, and you could ask, can I obtain something polynomial in log of 1 over epsilon? That would be better. Well, no. Also, in that case, you would have proven P is equal to NP. And another thing that you could wonder that I find a little bit ugly in this statement is that you're assuming, you might have noticed, that we have a bounded MIQP, which tells me that, well, I need to know that it doesn't go to minus infinity right up front. And unfortunately, also, this assumption cannot be bounded. In fact, even under these assumptions here, this fixed K and P, deciding, just the problem of deciding whether this is unbounded or not is NP hard. So we cannot do that either. Good. So that's our statement. And so in the rest of the talk, I want to tell you a little bit about our algorithm. Just again, I'm going to hide most of the things under the carpet. I just want to give you the geometric ideas, and so to have you see the techniques that we use. Okay, so the first thing is a change of basis. So it's a change of basis to put our problem in a form that we like more. So we want two properties that have been used in the past in several of these results, also in mixed integer linear programming as well as quadratic programming. So the first thing we want is a separable objective function, as we discussed, is also required in some other statements we saw before. So what does it mean? That instead of having our quadratic part of the objective that is just some x transpose qx, we want to have in the new variables y transpose dy for the diagonal. So essentially we don't want terms xi xj, we only want terms xi square or linear in xi. Okay? Good. So that's the first thing we want in our wish list. The second thing we want is that our polyhedron is of what we call spherical form, which means that it is sandwiched between two balls with the same center, let's say the origin, and with the radii that are a polynomial scaling of each other, polynomial in n, let's say. And again, we know, so what do we know? This we know very well from it's a key property that is used like in Lestra's algorithm in integer linear programming. So we know how to obtain this transformation in polytime. We also know how to obtain a diagonalization of Q of this form, which is essentially a symmetric decomposition of Q. This can be done in polynomial time. What is tricky here is to do both things at the same time. And this is related to questions about simultaneous diagonalization of matrices and whatnot. And it's particularly tricky because most of the literature in this direction, even just about symmetric decompositions and so is not really interested in polynomial time algorithms. They're interested in having a polynomial number of iterations, but who knows what happens to the size of the numbers, which could result in exponential time algorithms. All right, so anyway, we are able to do something like this, or let's say equivalent to this. Again, here I'm kind of hiding a few complexities. Yeah.
Here for Q having this form, which as I understand it, the last line kind of wraps up what you're getting from 1 and 2 together, right?
I will want something like this, but had to be very special to obtain this.
Yeah. Okay.
Yeah.
But there, are you using the fact that the rank is bounded independent of n? Is that part of what you need for this part?
In a way, yeah. Why? Because I mean, is there a specific? Okay. So we don't, okay, since you're asking, we don't exactly obtain both things at the same time. We actually do something similar, but yeah, this essentially makes things look easier. So we don't have a precisely this thing. We do something that needs the fixed rank. So we're still kind of interested in understanding if we can do this kind of cleaner in a way, more like this. So yeah, if we want, we can talk, would be nice. So for example, one way to obtain this transformation, the change of variables, would be to obtain a symmetric decomposition of Q of this form, where the Frobenius of L is polynomially bounded. We don't really have it, but let's say we do, okay, so that we make the presentation easier. Good, so let's say that now we have this transformation. We apply to our problem, and as promised, the new problem that we call spherical form MIQP will have these properties that we like. So in particular, it has, now we call the variable still x, so it has this separable objective function, and I also assume that D1, so the first the first variable has the largest absolute value, is the most curved, let's say, direction of the quadratic. Then we also have that our new polyhedron, which I still call ax less than or equal to b. I'm assuming that now it is in spherical form, and the inflation factor is n to the 3/2, for example. The price we need to pay, which is kind of a small price, it doesn't really matter, is that our beautiful zp times rn minus p is now a little bit messed up. We obtain what we call like a mixed integer lattice. It's just a this set after some affine transformation. So nothing more than that, just a little bit uglier. We call it lambda. So that's the problem we're going to work with, S-MIQP, spherical form MIQP. So and the first thing we do is immediately use the larger sphere that contains my polyhedron to apply one of the most well-known techniques in quadratic in discretization of quadratic functions, which is mesh partition and linear underestimators. So what we do is we look at our two spheres here, and we look at the largest one, and we partition it into phi to the k cubes. So phi is a number that we need to understand later what we need. And why to the k and not to the n? Because, well, I'm not really doing this partition in every dimension. I only needed to do it in the k directions where the quadratic is nonlinear, because that's what I want to linearize. Good. So you can imagine, right, these cubes to be like that. And now the idea is very simple. In each cube, I want to replace my quadratic function with the best linear approximation of it, and then kind of solve separately each problem, which is now a mixed integer linear programming problem. So now you see, thanks to our diagonalization and the fact that the grid is aligned with such a diagonalization, essentially, what happens is that there is a clear choice for the best linear approximation of your quadratic. For example, let's say this is my quadratic, this is a cube, and you see what happens is that there's a unique affine function that touches the quadratic on the extreme points of the cube. And this is a very special, right? Because in general, you pick three of them, you have a plane passing through them, and the fourth would be off. But thanks to our assumption, this doesn't happen. And this allows me to obtain this linear function that nicely approximates my original quadratic. And it's essentially off only by this factor. I don't really mind. I mean, let's not focus too much on what this number is. We can call it for now our magic number. We will see it again later. Good. So now that's what we have to do, right? We solve in each cube the original problem where the quadratic is replaced with our linear approximation. And what we do is we solve all of them, which now each one can be solved in polytime because it's a mixed integer linear programming problem with a fixed number of integer variables. So we can use Lenstra's algorithm to efficiently solve this in polytime. So we solve all of them, and we keep the best solution among all the ones we have found, all the optimal solutions of them. We just keep the best. Okay, in total, we have solved the phi to the k mixed integer linear programs. So, of course, we would love if this is an epsilon approximate solution to our problem. Of course, it's not. It's not always, but let's see what we would need to prove. It is an epsilon approximate solution if the definition holds, which is this one. It's this inequality. So what we can do to prove it is, for example, prove that this is small enough and this is large enough in such a way that this inequality holds. So we're going to prove separately these two bounds. And the upper bound for this is extremely easy. It follows directly from our approximation of the quadratic with the linear function that we just discussed. And in fact, that property immediately tells you that this quantity that we just want to upper bound is precisely upper bounded by the magic number we saw before. So that's easy. What is more complicated is to obtain the lower bound. So what exactly do we need to lower bound? The overall gap of the objective function on the full feasible region. Okay, so this what I write as obj max minus obj min over the feasible region. So we want to show it's large. So what's the idea? What's the idea? The idea is, you see, let's go back to our, here. Forget that we're looking at the discrete case. Like, think about all the points being feasible. Now we know that the function is the most curved along the x1 direction by construction. And what happens is, so if you just look at the x1 axis essentially intersected with this the inner sphere where all the points are feasible, it turns out that you can pick 3 points equally spaced along this axis, and due to the fact that the function is kind of very nonlinear, you will obtain a bound on how much these 3 points vary, and this will be enough to obtain the bound that is good for us. Of course, this is not going to work in general because, well, if you pick 3 points aligned along here, they will not be mixed integer, right? Generally, yeah, with probability 0, they will be. So what is the idea is to relax a little bit our requirement. Instead of searching for these 3 points aligned along the x1 axis, we search for them almost aligned. So how? We want them far away in the first direction. We want them very close in all other directions, in all other components, and that's the property 2 here. And finally, well, we want all three points to be feasible, the 2 points and the midpoint. And for example, you can just ask that 2 points are in twice your mixed integer lattice so that the midpoint will be in the lattice 2, like the midpoint between 2 even numbers is an integer, right? So now if you have, in fact, this what I call aligned vectors, then you can essentially do the same type of argument I discussed in our idea and obtain this bound, which is good for us. It's still good for us. Now, so let's look at this case where we have these aligned vectors. Now, which means we have now these 2 bounds, and the key thing that is going on here is that they're both linear in D1. So D1 simplifies, and you can just choose your phi, you remember it, which tells me how many cubes I need to be this number. Okay, which means that since we solved the phi to the k mixed integer linear programs, for the approximation, we only solve this number of mixed integer linear programs, which is a good number for us. Why? K is fixed, and so this is polynomial in n and 1 over epsilon. So that's what we want, okay? So great. If we have these aligned vectors, we're done. But what if we don't? Well, not only that, but how can we check if we have aligned vectors? And here's really the last part of our algorithm. We claim that there is a polynomial time algorithm which either finds 2 aligned vectors or partition my problems into a polynomial number of sub-problems which look the same, but with 1 fewer integer variable. So you see, if you have this proposition, now we discuss why this is true, but then we have a recursive algorithm, right? Think about starting from your problem, you apply this proposition. If you find the aligned vectors, you're done immediately with your approximate solution. Or if not, you partition your problem. Think about creating a tree. You create a bunch of sub-problems. For each one, you repeat this proposition and either you partition or solve. At the end of the day, since you have only p integer variables, and at each every time you partition, you decrease that by 1, the total number of mixed integer linear programs you solve is this number we just discussed, times poly n to the p, which since p is fixed, is polynomial in n, so it's good. Okay? So now, how is this proposition true? Well, again, I give you a picture. So remember, that's our definition of aligned vectors. That's what we're searching for. So let's look at this inner sphere inside our polyhedron. And I construct these 2 smaller spheres, one fully to the left and one fully to the right, with the radii, let's say, 1/4. Now you see, if I find a point here inside this sphere, and one inside this sphere, I automatically satisfy condition 1 and 2. The problem is the third, about being in the mixed integer lattice. But here's where I can use Lenstra's algorithm. So essentially, Lenstra's algorithm tells me that there is a polynomial time algorithm that either, so let's focus on this sphere, either finds a point inside here in my mixed integer lattice, let's say 2 lambda, or it proves that this is flat. So it means that it gives me a direction that allows me to partition all the feasible points inside of it with a few parallel hyperplanes. Okay, so now the idea is to apply Lenstra both here and here at the same time. If in both cases I find my point, I am done because I have my aligned vectors. If not, then at least one of these two spheres is flat, like this one, but then so is the sphere B01 because of this is just this has radius 1/4, and that's 1. So just multiply by 4 the number of hyperplanes, and you can also partition all the points in this bigger sphere efficiently. But then remember, our polyhedron is much bigger than that, right? It's actually contained in B0 n to the 3/2. But again, that's just a polynomial inflation. So then, essentially, from the fact that this one was flat, this sphere, also the largest sphere is flat. And essentially, I have now these hyperplanes, these parallel hyperplanes. Each one, I now take the restriction of my problem to each separate hyperplane. And this is essentially like the original problem, but in one fewer dimension and critically with one fewer integer variables. And so that's how this works. So yeah, that's all I wanted to tell you today. Let me know if you have any question or counter examples. Thank you.
Questions for Alberto?
Yeah, I was just wondering. Maybe there's for this algorithm, this approximation scheme, what if I had, instead of like quadratic function, low rank, I have like some other really nice function of a projection into a low dimensional subspace. And I know what that projection is. So I know what that, so I could diagonalize like you're doing, and then I can do piecewise linear of this other nice function that's around it. Does that make sense?
So you're asking essentially if you have a lower dimensional objective function plus some linear space. Yes.
Quadratic with something
Some well-behaved.
that's in a sub. So I have inside, you have a nice function. It's not quadratic, but it's super.
Yeah.
Super. And then it's a function of some vector in a subspace. If you know what I'm saying.
Yeah, so I mean, some properties that we use are for quadratics only, but probably you can replace with the corresponding assumption. For example, probably some Lipschitz continuity would work, and you could be able to obtain something similar in that case. Yeah.
Other questions? I'll ask a question. So, Mr. Computing Society winner, when are you going to implement your algorithm?
Wait, no, I'm not going to do that. That's why I have my colleagues here to help me out.
Well, please, let's thank Alberto for his very usual, very enlightening and interesting talk.
Thank you.